Hello everybody, and welcome to our first video of Chapter 9. Chapter 9 is going to be all about parabolas and quadratic equations. So we're going to start this chapter by looking at some applications of quadratic equations and parabolas so that we can see why we might want to learn about them. What we're going to do today is start by reviewing some models that we've already learned about, and that would be linear and exponential models. Then we're going to look at some features of this new model that we're going to be discussing. So let's start with linear models. When we first learned about linear models, we said that the patterns you look for to determine that you're supposed to be using a linear model would be an adding or subtracting pattern. So we're going to use a linear model when the same value is being added or subtracted from our initial value every single time. For exponential models, we said the patterns you look for are multiplying, dividing, and percentages. And all three of those patterns would let us know that an exponential model was appropriate. Now, when we write a linear model equation, the equation looks like this. Y equals mx plus b, where m was the repeating value. This was the thing that was being added or subtracted every time, and b was the initial value. It was a one-time thing, and it was your starting amount. When we learned about exponential model equations, we said the equations look like this: a times b to the x, or a times 1 plus or minus r to the t, depending on what type of pattern you have. If you have a multiplying or dividing pattern, then you use this guy. And if you have a percent pattern, then you use this guy. Now, in the first equation, the a is your initial amount. And it's the same thing in the second equation. The a is always going to stand for your initial amount or your starting amount in that problem. The exponent is always going to be the variable. So x or t, they're both the variables. The only thing that changes is the base that we use for that exponent. In this problem, in this type of equation, this is the multiplying pattern. So if we were multiplying by 2 every time, b would be 2. Whereas in this equation, because we're dealing with percents, to figure out that base, the r is the percent as a decimal. So we needed to convert all of our percents to decimals. Finally, we discussed the types of graphs we might see. So when we have a linear pattern, a linear model with an adding or subtracting pattern, we might end up with a graph that is going uphill if we are adding the same amount every time. Or we might end up with a graph that is going downhill if we are subtracting the same amount every time. So this would be for your adding patterns, and this would be for your subtracting patterns. If we have an exponential model, we said we also have two different types of graphs we could have. We could have a growth model, which could be getting farther away by going up, or could be getting further away by going down. And we could have a decay model, which is when our numbers were decreasing or getting smaller. So for our decay model, we could have a pattern that's going down and getting closer to the x-axis, or up and getting closer to the x-axis. Either one of those. So what are we going to be learning about in this chapter, now that we've kind of reviewed that part? We are going to be learning about quadratic models, or graphs that look like parabolas. The pattern you're going to look for is that something in the problem goes up and then comes down, or goes down and then comes back up. In other words, there must be a turning point somewhere in the problem. At some point, the object that you're observing, or the person or the behavior that you're observing, turns around. It switches from going down to up or up to down. So what would these equations look like? Well, there are two different types of equations we're going to look at. We're going to look at what's called standard form, and we are going to look at what's called vertex form. Both of these equations describe parabolas and our quadratic models. They're just helpful for different reasons. So standard form looks like this. Y equals ax squared plus bx plus c. And vertex form looks like this. Y equals a parentheses x minus h parentheses squared plus k. We're going to learn a lot more about these specific types of equations in the next couple days, but for now, you're just going to be asked to analyze a graph when it's given to you. So you're just going to need to sort of know when you see these that these are quadratic. The thing that makes these quadratic is that they have a squared as the highest power. Anytime your highest power is 2, you know you have a quadratic model and you know you have a graph that looks like a parabola. So what do these graphs look like? Well, just like the other graphs, there are two options. We can have a parabola that opens up, and we can have a parabola that opens down. So let's draw a couple examples of an upward-facing parabola. An upward-facing parabola could look like this. It looks kind of like the letter U, it's just opening up. An upward-facing parabola could look like this. It could kind of be shifted around. It doesn't really matter where it's located. The thing that they have in common is that part goes down and part goes up, and there's a turning point there right at the bottom. Now we could also have a downward facing parabola. So a downward facing parabola would look like this. It looks like a frown. It's facing down. It kind of rhymes. And then it could also look like this. Could be anywhere on the graph. It's always going to be facing down. So instead of going downhill and changing to uphill, these graphs would go uphill and change to downhill. But there's always a turning point in there. So what are you expected to be able to do? Well, at this point, what you should be able to do is look at the graph of a parabola where some information may be labeled and answer questions about the real-world problem that it's describing. So for example, here it says the height h in meters of an object above the ground is given by h of t equals negative 16t squared plus 64t plus 190 for t is greater than or equal to 0, where t is the time in seconds, and a graph of the model is shown. So let's break this down before we start working on answering questions. What do these directions really mean? It's telling me that in this problem, h stands for the height in meters, so it's telling me what h stands for. And you'll notice height in meters is labeled on the y-axis here. It's also telling me that t is the time in seconds, and you'll notice that time in seconds is labeled on the x-axis here. And it tells me that t is always greater than or equal to 0. Now what that means is that when I'm looking at the x-axis, I don't care about the negative numbers. If time has to be bigger than or equal to 0, I don't care about having times that are negative answers, like -1. So, since this is already graphed for me, I'm just going to have to be able to read the graph and tell me what it's saying about the real world situation. So, if I look at the question, the first question, A, says, what is the maximum height reached by the object? So, maximum height means the highest it goes. If I look at this graph, it looks like the object goes up and then comes back down. So, it's going to reach the maximum height right here. That's going to be the highest spot. Now, the highest it actually goes would be whatever y value corresponds to that point, which it says here at this point that's labeled is 164. And 164 is a height which in this problem is measured in meters. So I would say 164 meters. Part B says, how long does it take to reach the maximum height? So if I want to know how long it takes to reach the maximum height, that's really the time. So what time is it? In other words, what is the x value when I get to this height? Well, according to this ordered pair, the maximum height would happen when the time is 2. And in this problem, time is measured in seconds, so I would label that S for seconds. Next it says, when does the object land? Well, the object's going to land when it hits the ground. So since the ground is going to have a height of 0, I'm going to look for where the graph has a height of 0, which is right here. Now it says here at this point that's labeled that the x value, or the time there, is 5.202 seconds. Next it says, this object was originally launched from a platform, and that platform was how high when it was launched. So when it says originally launched, that means the time would be 0. So at the very beginning of this experiment, when time was 0, nothing has happened yet, how high was it? Well, time is on the x-axis, so the time is 0 here, and the height there would be 100. Now, since heights in this problem are measured in meters, it would be 100 meters. And lastly, it says how long was the object above 100 meters? So I have to first figure out which section of this graph is above 100. So here's the 100. Everything above this line is going to be above 100 meters. So this whole section of the graph is above that line. Now, that means I'm above 100 meters from 0 to 4 seconds. From 0 to 4 seconds is a total time of 4 seconds. So I was above 100 meters for 4 seconds of time. For problem number 2, it says the depth d in meters that a dolphin dives while swimming is modeled by this function where t is greater than or equal to 0, where t is the time in seconds. A graph of the model is shown. So again, it's telling me the depth is measured in meters, the time is measured in seconds. The first question is, how low does the dolphin go? What is the lowest the dolphin dives below the water? Since the x-axis is here, you can see that the dolphin is going below there, which is why his heights are negative. He's below water and coming back up. So the lowest it goes is going to be this y value, which is negative 100 meters. Now if I say what is the lowest the dolphin goes, instead of saying negative 100, I would change that to 100 meters below the surface. It's very important to realize that when I say what is the lowest it goes, saying negative 100 sort of sounds weird because we don't usually measure heights in negative numbers. So we have to change this negative and make it positive and then just describe it as below the surface. If it says how long does it take the dolphin to resurface? So resurface means reach the surface of the water again. So the surface of the water is here. It looks like I reached the surface of the water again here where the x value is 8.472 seconds. So I was below water for the dolphin was below water for 8.472 seconds. At what time does the dolphin reach its maximum depth? So maximum depth means the lowest it goes. The lowest it goes happens when the t is 4. That's the x value of that ordered pair. So I would say 4 seconds. The dolphin was swimming underwater before it started to dive. At what depth was the dolphin swimming before it started its dive? So since it says here that my time starts at 0, before I started my dive would mean when t is 0, because that's the beginning. So when t is 0, the depth of the dolphin is 20 meters below the surface. And next, at what time did the dolphin reach a depth of 80 meters? So when the depth is 80 meters, which is here, I want to know when the dolphin reaches that level. It looks to me like the dolphin's going to reach that level twice. Once when the time is 2 seconds and again when the time is 6 seconds. So I would say 2 seconds and 6 seconds. And finally, the last question says, how deep was the dolphin after 8 seconds? So if I want to think about how deep the dolphin was after 8 seconds, that is a time. So I'm going to go to where the time was 8, which is here, and I'm going to look for how deep the dolphin was. Now the y value there is -20. So I would say 20 meters below the surface. Because remember, we never want to list, you can't really see what I wrote there. We never want to list heights as negatives since it doesn't really make sense. So instead we see that negative as meaning it was below the surface instead of saying it was a negative height. All right, that wraps it up. Thank you guys so much for watching and have a great night.